Hello to everybody, this is Corrado Loglisci from University of Bari, Italy, and the work I'm going to present is a contribution on process mining. In process mining we have process models which generalize the traces, which are sequences of activities performed by the actors in the context of complex systems, technological platforms, or informative systems. So those traces should be compliant with the process models, which are assumed to be stable over time. And any trace should be adhered to those process models. Anyway, in real-world application, in real-world informative systems, there could be deviant traces, there could be deviant activities which can make the process models obsolete. So, the informative systems are required to account for those, are required to, in particular, either keep the process models update or build new process models. To do this, it's necessary to have the occurrence time when the deviation occur and a description of those deviation, of those changes. In the state of art, most of approaches face only the first sub-problem, the identification of occurrence time, while in this work we deal with both sub-problems, namely the identification of occurrence time. We termed it as process drift detection, and the description of the changes, the description of the process drift. We termed it as process drift characterization. This is done in the context of an unsupervised setting, which does not assume the existence of the supervision, which does not assume the availability of the so-called labeled drift, labeled changes. That's it. So the proposal we have is based on the following key points. We use frequent patterns as a summarizing form to generalize the traces, to generalize the sequence of activities. So the process models are built upon the frequent patterns, which in this way depict whatever happens as frequent behavior in the underlying traces by discarding what is sporadic. So any deviation, any change occurring at the level of traces can be reflected at the level of patterns as frequency-based changes, which in their turn can be reflected at the level of process models in terms of pattern-based changes. The use of frequent patterns also allow us to work at a high level of the data instead of operating at the level of raw traces, at the level of raw activities. So we keep in mind these three items. A crucial point of this solution is the representation of the traces. The original representation, the sequences, is a monodimensional structure which does not allow us to account for two kind of changes: the changes over traces and the changes over activities. For this reason, we propose to use graphs, simple graphs, shades, as a time dimension, 10-dimensional representation. So to face the three items I mentioned before, patterns, their frequency-based changes, and their pattern-based changes, we resort to the class of pattern-based change detectors, working on dynamic networks. In this case, we have dynamic chains. In particular, we adapt an algorithm karma we proposed in this work. In particular, it tracks changes by working on pairs of time windows, by detecting changes as dissimilarity emerging, by matching the patterns discovered in a time window against the pattern discovered in the second time window. In particular, our revision of karma, namely karma 3, analyzed the traces in a data stream fashions by acquiring blocks of traces. So it mines frequent chains from couples of non-overlapping time windows. This corresponding to patterns discovery item I mentioned before. Once we have done this, we search for interesting changes, significant change on those patterns in terms of significant changes in terms of frequency based changes on those chains. This corresponds to the frequency-based changes I mentioned before. Then we use those significant changes to compute a Joker-based Similarity Score on those time windows. Then, if that dissimilarity score exceeds a user-defined threshold, then we have detected a process drift. So we can continue the analysis with two new time windows at all. Otherwise, we don't have a process drift, and we can update our current data by extending the first time window and with a new second time window. Other technical details: karma 3 represents chains in form of subtrees. This is done to account for changes triggered by any activity we can have in our traces. So we can consider any activity as a root of our subtrees. And karma 3 returns not all the subtrees having frequency-based changes, but only those which are maximal, namely the longest chains with frequency-based changes. That's it as to the computational solution. We performed experiments, a comparative evaluation with the three well-known competitors, Bose, and two versions of ProDrift, well known in process mining. We did this evaluation with 10 synthetic event logs we generated. So some results. In this slide we have results in terms of accuracy, namely the ability of the algorithms in detecting ground truth process drifts. As you can see, we have karma tree at different experimental configurations. We have ProDrift in its optimal configuration, namely with fixed time window. In this case, we have ProDrift with adapted time window. As you can see, we have comparable performances in terms of accuracy. I mean, as to ProDrift with fixed time window, while Karma tree outperformed the other variant of ProDrift, and the same happens with Bose. So we have quite comparable quite comparable accuracy with the best competitor. We have less running times. Karma tree is more efficient in terms of time consumption. Just to give you a practical illustration of the ability of Karma tree, we studied a real-world application on traces obtained by an informative system recording traces on medical services billing by from a Dutch hospital. We used the competitor heuristic on those traces, and it detected two separated process models, which anyway can be independent each other. These two models, I mean. Why? Karma tree was able to detect the process drift concerning those process models, and additionally it characterized that chain of activities by revealing that it was frequent in this second time windows and infrequent in this first time window. That's it. So to conclude, in this work we investigate a well-known problem in process mining from a more comprehensive perspective. We have quite comparable accuracy with more efficiency in terms of running times. As future work, we are planning to consider more complex representation of the traces by considering actors, resources, and so on. So that's it, and I thank you.